Hi, this is your video for sections 10.2 and 10.3 about hypothesis tests for population proportions and population means. So one more time we're going to go through the steps for a hypothesis test, and then we'll look at each step in more detail. So step 1 is to determine the null and alternative hypotheses. Step 2 is to choose the level of significance, alpha. Step 3 is to compute the test statistic. Step 4 is to find the p-value and determine the initial conclusion. And step 5 is to state the final conclusion. So step 1, and again we've already talked about this in the last section, but it's worth going over again. Step 1 is to determine the null and alternative hypotheses. So the first thing you need to do, and this is actually the beginning of your hypothesis test, is to write down the claim or the statement being made. And this should be in a complete sentence. Then we want to translate the claim or the statement into an alternative hypothesis by answering these questions. First, what parameter is being tested? In this chapter, it's either going to be a mean or a proportion, so you just have to determine which of the two it is. For a mean, the notation we'll use is mu. For proportion, we'll use p. Then, what inequality should we be using? And for the alternative hypothesis, it has to be an inequality with no equals included. So it's either a less than, a greater than, or not equal to. The third question is, what is the value of the parameter stated in the claim? This value that we use in the hypotheses never comes from the sample data. Once we have answered those three questions, then we can translate the answers into the alternative hypothesis in symbols. So we have our symbol, either the mu or the p, the inequality, and the number. Now once we have the alternative hypothesis, we can write the null hypothesis just by replacing the inequality with an equal sign. So we're going to go through one example of hypothesis testing and go through all 5 steps. So the first step for this problem would be first to write the claim as a complete sentence. So here where it says a researcher claims that the mean length of a call has increased since then, we want to put all the details into our statement. So we'll say the mean length of a call has increased since March 2006 when it was found to be 3.25 minutes. So this tells us what parameter we're talking about, the mean. This talks about how it has changed, that it's increased, and it also has the value 3.25 that we need to know. So we want to translate this statement into our alternative hypothesis. What parameter are we testing? The mean. So we're going to use the symbol mu. What inequality should we use? Increased translates to a greater than because it's gone up since March 2006. And the value of the parameter in the claim was 3.25 minutes. So we just take those 3 things and write our alternative hypothesis. So we have mu is greater than 3.25. For our null hypothesis, we replace the greater than with an equal sign. So there's our null hypothesis and our alternative hypothesis. Step 2 is to choose the level of significance, alpha. And in most of the homework problems you'll do, this is already chosen for you. But if you do have to choose this, you want to base your decision on the seriousness of the consequences of making a type 1 error. The more serious the consequences, the smaller the significance level alpha should be. The 3 typical values that we see are 10% or 0.10, 5% or 0.05, and 1% or 0.01. Back to our example. We already found our null and alternative hypotheses. Now we're going to find our significance level. This was already chosen for us because the problem tells us to test the claim at a 5% significance level. But we do still have to state what that's going to be in our hypothesis test. So for step 2, we would write alpha equals 0.05. Now step 3 is to compute the test statistic. So here's where we have to choose the right formula depending on what parameter we're testing. So it makes a big difference here whether we're testing a mean or a proportion. For a mean, we're going to use this formula. So this is T naught, this is X bar, which comes from our sample. That's our sample mean. This is mu sub 0, which comes from our hypotheses. S is our sample standard deviation. N is our sample size. If we have a proportion, then we're using Z sub 0, and here we have P hat, which is our sample proportion, P naught, which is coming from our hypothesis. That gets used in 3 different places, and then the N is our sample size. Now in both of these formulas, the symbol on the left side, the T or the Z, tells you which distribution to use. So in this one, this tells you you're using the T distribution. This one tells you you're using the standard normal distribution. So it's important when you're computing this test statistic to write down the whole formula, including the part on the left side. Now the problem we usually run into is figuring out which numbers go where. So on the right side of these formulas, anything with a subscript 0 is going to come from your hypotheses. So that's the number that you used in your null and alternative hypothesis. Anything without a subscript, so the X bar, the S, the N, and here the P hat and the N, those are going to come from your sample data. Back to our example. In this problem, since we're testing a mean, we're going to use this formula to compute our test statistic. So the mu 0 comes from the hypotheses. Since our null hypothesis was that mu is equal to 3.25, the number that we want to use for mu sub 0 in the formula is the 3.25. The other numbers in this formula all come from the sample data. So we were told that the sample has a mean of 3.42, that's our sample mean, a sample standard deviation of 0.9, so that's S, and the N was 81 because we had a sample of 81 cell phone calls. So we're plugging all of those numbers in, and remember your sample mean comes first on the top of this formula, and this again is the number from our hypothesis. So if we do those calculations, we come out with T0 equals 1.700, and that is our test statistic. Now step 4 is broken into 2 parts. Part A is to find the p-value, and this is a different p than the other p's we've talked about. I know it gets confusing with all the p's in this class. So the first part of this is to figure out which type of test you have by looking at the alternative hypothesis, H1. So this just depends on which one of those 3 inequalities you used. If you used a less than, then you have a left-tailed test. And notice this one's pointing to the left. If you have a greater than, which points to the right, then you have a right-tailed test. And if you have a not equal to, you have a two-tailed test. Now what you want to do is draw a picture of your distribution, either the t distribution or the standard normal distribution, and plot the test statistic on there. This doesn't have to be perfect, just make sure that the test statistic is on the correct side of 0. For a left-tailed test, you want to shade the area to the left of the test statistic. For a right-tailed test, you want to shade the area to the right. And for a two-tailed test, shade the area for the tail, whichever side of 0 the test statistic is on. So it's to the left of 0, then you shade to the left. If it's to the right of 0, then you shade to the right of it. Okay, here's some pictures to illustrate what we're talking about. If we have a left-tailed test, then we're going to take our test statistic and plot it on our distribution picture, and we're going to shade to the left of that. Now to find our p-value, it's going to be the probability of this area in the left tail. So it's the probability that t is less than this number or that z is less than this number, depending on if we have a t distribution or a standard normal distribution. But they both look pretty much the same. Now if we have a right-tailed test, we have the opposite situation. Then we have our test statistic over here, and we're going to shade to the right of it, and then we want to find the area in that tail. So we're finding the probability either that t is greater than this number or that z is greater than this number, depending on which distribution we're using. Now if we have a two-tailed test, then we're going to look at the area in both tails. So this one is a little bit harder to understand. If we have a two-tailed test, then we look at the value of our test statistic. If our test statistic is negative, that means it's to the left of 0, then we're going to find the area in this left tail, and then our whole p-value is going to be that area plus the corresponding area in the right tail. So we just find the area in the left tail, and we multiply that number by 2. If our test statistic is positive, that puts it over here to the right of 0. So in that case, we're going to look at the right tail, find the probability or the area for that tail, and then we multiply that by 2. So it just depends on where your test statistic is. If it's negative, then you find the left tail. If it's positive, you find the right tail, and either way, you multiply that answer by 2. Back to our example. Our alternative hypothesis in this problem was that the mean is greater than 3.25. Since this inequality is pointing to the right, this makes it a right-tailed test. And in step 3, we found our test statistic was 1.700. So here's our picture. Since we have a right-tailed test, we're going to be shading to the right of our test statistic. So here's our test statistic is 1.700. So what we're doing is finding the area in this right tail. Or we can think of it as finding the probability that t is greater than 1.700. Now for this, you can use the t-CDF function in your calculator. This works like the normal CDF function in that we put in a lower bound and an upper bound. So since we're going from this number to the right, this would be our lower bound, and we'd use a large positive number for our upper bound. The only difference here is that we don't need mean and standard deviation, we need degrees of freedom. So again, the degrees of freedom here is n-1. Since our n was 81, then our degrees of freedom is 80. So if you put this in your calculator, you should get something like 0.0465. So that is our p-value. In other words, that's the area that's shaded in blue over here in the right tail of this distribution. The second part of step 4 is to take that p-value and use that to determine the initial conclusion, which is going to be in terms of the null hypothesis. So to do that, we're going to compare the p-value we came up with in part A of this step to our alpha, which is our significance level. And what we're going to do is look at this inequality. P, which is our p-value, is less than or equal to alpha. So we're going to plug our p-value in on this side, our alpha in on this side, and then we determine whether this inequality is a true statement or a false statement. If it's a true statement, then we'll have a positive conclusion. And the way we state this in terms of the null hypothesis is that we will reject the null hypothesis. And I put the do in parentheses here because we're saying this is a positive conclusion and that we do reject the null hypothesis. Now if this inequality up here is false when you plug in the p-value in the alpha, then we'll have a negative conclusion, and we'll write that as do not reject the null hypothesis. So this one was the positive because we have kind of an understood do in there, so we just say reject the null hypothesis. This one is negative because we say do not reject the null hypothesis. Okay, so back to our example. In step 4a, we found that the p-value was 0.0465, and the significance level that we had in step 2 was 0.05. This is one reason it's important to go ahead and write that down in step 2, because if you don't have it written down, then you have to go back to the problem and look it up again, or figure out what you had decided on for your alpha. If you have it written down in step 2, then you don't have to do any extra work. So now we're going to compare this p-value and the alpha. So the inequality that we're looking at is p is less than or equal to alpha. In this case, here's our p-value, here's our alpha. So the question is this a true statement or a false statement? It's true because 0.0465 is less than 0.05. So since it's true, that means we're going to have a positive conclusion, which is reject the null hypothesis. This is all we need to write for our initial conclusion, either reject the null hypothesis or do not reject the null hypothesis. Now step 5 is to state the final conclusion. And again, this is either going to be positive or negative. So if we had a positive initial conclusion, then we'll have a positive final conclusion. And this will say that there is sufficient evidence to support the claim that, and here we just restate the claim and make a complete sentence. So we can take the claim that we stated in step 1 and just copy it in here. Now, if we had a negative conclusion in step 4b, then we'll have a negative final conclusion. So a negative final conclusion would say there is not sufficient evidence to support the claim that, and again here we restate the claim just like we stated it in step 1. So again, positive is saying that there is sufficient evidence to support the claim. Negative is saying there is not sufficient evidence to support the claim. In our example, in step 4b, we had a positive conclusion which said reject the null hypothesis. That means our final conclusion will also be positive. And the claim that we stated in step 1 was that the mean length of a call has increased since March 2006 when it was found to be 3.25 minutes. So we're just going to take this and restate it. And our final conclusion will say there is sufficient evidence to support the claim, and then we're just restating this claim right here. So there is sufficient evidence to support the claim that the mean length of a call has increased since March 2006 when it was found to be 3.25 minutes. Again, a positive conclusion, again, a positive initial conclusion of reject H not leads to a positive final conclusion saying there is sufficient evidence to support the claim.